Welcome to the deep dive. Today we're digging into discriminant analysis. Ever wondered how you can automatically sort things into distinct groups just based on data? Well, that's pretty much the core idea, and it's actually incredibly useful. Our mission today, pretty simple. Cut through the jargon, get a solid handle on what discriminant analysis is, how it works, and where you might bump into it. Think of it as your fast track to understanding this classification tool.
Exactly. Yeah, the fundamental goal is really to take a data set you have and effectively separate it out into these different sort of predefined groups or classes.
Okay, so how do we actually do that separating? I keep hearing about linear discriminant analysis, LDA. What's the heart of that?
Right, LDA. So LDA does this by finding the best linear way to combine your data's features. The aim is really to maximize the separation between the averages of the groups, while also keeping the spread within each group as small as possible. Like imagine drawing straight lines to best divide different clusters of data points you see.
Straight lines, okay, got it. Are there any situations where that might not be the best approach?
Oh, definitely. LDA works best when the data within each group is, let's say, roughly normally distributed. And also when the variability, the spread within each group is pretty similar. If those conditions aren't really met, yeah, we might need to look at other methods.
Like logistic regression. I know that's also used for classification tasks. What's
Yeah.
the key difference there then?
Well, the main difference really lies in the assumptions they make. LDA, as we said, assumes the predictors, the data you're using, are normally distributed within each class. Logistic regression, though, it doesn't need that assumption. It directly models the probability of belonging to a certain class.
Ah, okay. So LDA is maybe more about the inherent structure of the data itself. Now, what about this discriminant function I've heard mentioned? What role does that play?
Good question. The discriminant function is, it's the actual equation that LDA creates. It takes your data points, your observations, runs them through this specific equation, and it basically spits out a score. And that score tells you which of the predefined groups that data point most likely belongs to. It's the tool that actually does the classification.
Makes sense, the practical part.
Right.
So, okay, how do we know if this tool, this function, is actually working well?
We usually evaluate its performance by looking at how accurately it classifies data points into their correct groups.
Yeah.
Often we test this on data the model hasn't, seen before to get a fair assessment.
Right, testing it.
Huh.
You also mentioned quadratic discriminant analysis earlier, QDA. When would that be more useful than LDA?
QDA. Yeah, that comes into play when that LDA assumption about equal variability or equal covariances across the groups doesn't really hold true. So if the spread or maybe the relationships between features are quite different between your groups, QDA can create more flexible kind of curved boundaries to separate them instead of just straight lines.
So it handles more complex patterns.
Huh?
Okay. What if our data has features that are, like, highly correlated? What's that term again?
Multicollinearity, yes. That can definitely be a challenge. It can make the results from discriminant analysis a bit unstable and frankly harder to interpret reliably. When features are too similar, telling you basically the same thing, it gets tough to figure out which one is truly driving the separation between groups.
Right, because they're not giving you independent information.
Okay.
Now, there was another term that sounded interesting. Mahalanobis distance. What is that about?
Yeah, Mahalanobis distance. Think of it as, let's say, a smarter way to measure how far a data point is from the center of a group. What makes it smart is that it takes into account how the different features, the variables, in that group are related to each other, their covariance. So if two features tend to vary together, it accounts for that when calculating the distance. It's really useful for classification, for figuring out which group a new observation is closest to, considering the actual shape and spread of each group's data.
Interesting. So it's a more nuanced way of measuring closeness than just, say, straight line distance.
Mhm.
And can we actually see the results, like visualize this separation?
Absolutely. Often we can visualize the results. We can plot the data points in a simplified space, usually 2 or 3 dimensions, defined by those discriminant functions we talked about. This lets you visually assess, how well the groups are actually being separated by the analysis.
Okay, great. So bringing it all together then, discriminant analysis helps us classify data into distinct groups by finding the best ways to draw boundaries between them. LDA uses straight lines, generally speaking. QDA can use curves when needed. And concepts like the discriminant function itself and this Mahalanobis distance help us understand how it all works, sort of under the hood.
Precisely. You've nailed it. And it really makes you think, doesn't it? Considering how many real-world situations involve categorizing things, medical diagnoses, customer types, even spam filters, Where else might these core principles of finding separations be at play in your own areas of interest, even if the specific algorithms, LDA or QDA, aren't explicitly being named? Something to ponder.